Welcome everyone to the FE review session from CSULB, Tau Beta Pi Theta chapter. Good to see you all back. We have Secretary Anthony Cameron here as well, going to be joining us. And anybody else that is looking to be here live is also welcome to come. And if they do come, we will have fun solving problems, going through some statics today. Like usual, we will be going quickly through the FE handbook regarding this topic, and we'll be taking a quick peek at everything that they have in here so that everyone's familiar with what's provided, the specific equations, topics, if there's a problem you get where maybe you don't know the way to solve it, you may be able to figure out how to solve it just by going into the manual.
Hello. Good morning, everybody.
We have another guest here joining us, Mr. Ryan Valera. Welcome, sir.
Good morning, sir.
Just started our recording. We have Mr. Ryan Valera here. He's just recently passed the FE exam for mechanical, so it's a pleasure to have him here. He can give us some more insight on some of the potential problems we may be seeing on the future exams.
Yes, sir. That's quick. It's an honor to be in a workshop hosted by a Mr. Chigero, the one and only. So the pleasure is mine.
All right. Well, we were just about to go over the handbook for statics, so we can get a nice idea of what it's provided for us in the event that where we need something, so we know it's there. Cameras. It's very nice. Actually, is that being picked up? Hope it is.
What's up, Anthony?
What's going on?
Okay. All right. Let's take a look at this. So statics, right? This is the study of objects that technically don't move, hence the name statics. We deal a lot with forces, summing of forces, but in this regard, the sum of the forces is equal to 0, meaning no motion. We have a description of a force here. It's a simple definition. We have some I and J coordinates. We have resultants. You can find the resultant of a particular force by taking the square, or it's kind of like, Pythagorean theorem almost. You square the x component, the y component, and take the square root of them. You can also get the direction using an arctangent of the two forces as well. You can also resolve the forces into different directions, as it's detailed here. A lot of this stuff, at least here in the beginning, is maybe intuitive to you. You may not need a reference for small things like this. Moments as well, R cross F. A lot of these problems for statics deal with finding moments, summing of moments around specific points, axes, or structures. So that's pretty important as well. Systems of forces and equilibrium requirements for a system to be in static equilibrium. Okay. Centroids, masses, lengths, and volumes. I was talking to Mr. Cameron earlier about this. I hated these the most in terms of when I took my statics class, so I'll have a problem on this. We'll go through it. These are where you have some formulas that may be looking a little confusing, like this integral of x dA over a. Mr. Valera, you can confirm with me on this, but I don't think they would ask you a question that involved too much calculation. Like, let's say if they asked you to integrate for a moment of a, moment of a centroid or moment of inertia kind of thing. Is that did you see any questions on the exam that had you have to do like a lengthy integral calculation or something like that?
Yes. Well, there are a few problems where you have to do that, but they give you at the bottom of the static section, there's a table, and it has all the moments of inertia
for different shapes, correct?
Different shapes, right?
Right. Which in that case, so they basically would give you shapes that can abide by these rules, so you don't have to do the integration and derive it by hand, you're saying?
Correct. And the only ones you're pretty much gonna see on there, or at least that I saw, was somewhere over there. Those two you don't have to really worry about the moment of inertia about the x-axis. So I sub x
XC,
Yeah, and
like
there
for
were a couple about with the circles.
okay, moment of inertia about a circle,
Yeah,
like this one.
and then the concentric ones as well. I know I definitely saw that.
I see.
Hmm.
Okay, that's good to know. So yeah, basically they would rarely ask you to do a lengthy integral calculation just to prove one of the moment of inertia problems. So this is basically just as a definition. And something that you can be asked, I don't know if you were asked, but I've seen in some of the practice problems is conceptual problems that ask you, oh, what is the equation for the moment of inertia or the centroid of, this shape for, a general shape? And then you might be asked, this might be an answer choice, like integral of x dA over a or something like that. I've seen problems like that in the practice problems, and which may be fair game for the exam if they like that. Same with moment of inertia, second moment of area. This is integral of x squared instead of just x dA. Polar moment for polar coordinates, or a little bit more ugly looking. Parallel axis theorem. You use this when you want to move your central axis to, let's say, a different sections. This is a pretty good example here. You see your centroid is actually here. But if you had another section of this, maybe up here or something, another like a beam, an I-beam is another good, I'll draw. An I-beam is a good example. You have three separate, centroids for this thing. You got these three here. So if you wanted, if you calculated, like, let's say, calculated the one for here, you'd need to move your axis by d squared a, d being this distance between the next centroid you're calculating. And you'd be able to then get the moment of inertia of those two, and then you do the same thing for the third one. And then you could get the total combined moment of inertia for an I-beam. That's just an example, but that's what they would use a parallel axis theorem for. Radius of gyration, I believe, is not used very often, but it's just an equation where you use the moment of inertia in the area. You can get the radius of gyration for x, y, or p if you have a p dimension. Friction. Friction seems more, I guess we'd probably be dealing with static friction in this case, not quite the dynamic one. So if you get a question asking, what's the static friction required to hold this thing in place, or let's say the static friction is X, and what force will keep this thing from moving, kind of thing. Those may be considered dynamic problems too, but I guess it's dependent on what they're feeling at that time.
One note about that, Mr. Chair.
Oh, yes.
That friction equation, there's gonna be, I definitely saw one problem there, and there are a couple in the practice book, and it talks about you have to equate the friction equation to the centripetal force, I believe.
Okay. Is centripetal force is that in here? I wonder.
Yeah, that's the thing. They don't give you it in the book.
Yeah. Okay.
So you have to like actually know that one.
Centripetal force. Do you happen to remember?
No. Here, let me go get it for you guys.
Centripetal force, is that? I think that is has torque in it, or related to torque in any way. It is rotational.
Centripetal force.
What's Google tell you, Anthony?
Let's see if I can get an equation.
It'd be strange if they make you use that and it's not here.
Yeah. MAC equals mv squared over r times AC. Ultimately, it's velocity times, it looks like angular acceleration.
Oh.
Or velocity squared over r.
Centripetal force. Is that just force in rotational motion?
Yeah.
Which would be omega. Not omega. mass, which is the I, moment of inertia, A, what's acceleration in rotational coordinates? Alpha, I alpha.
All I know, there's definitely a couple problems in the book, but I don't know if it's in the statics or I think it might be in the dynamics portion.
No, it might be, that might be considered dynamics, because I'm pretty sure centripetal force is in dynamics section.
Right, but yeah, you have to equate it to this friction one.
Okay, that's good to know. That might be, they might use kinetic friction for that as well. Screw threads, for a screw thread. Screw loosening, screw tightening. I've never seen a screw problem in the practice, but they have it here, so I guess it is fair game. It looks like though it's just a equation that seems pretty straightforward, so hopefully if you get a question on that, you should be able to fall through with it. Belt friction. Oh, okay, so belt friction, I don't have it on our OneNote document, but there was a problem I had a belt friction, which is like a pulley. It was a pulley, but there was friction on the pulley and the belt, and you were asked to find the force that the resulting force on one of the sides. This one, basically, if you get a problem like this equation should get you through the problem entirely. It should give you a theta, a coefficient of friction, and you'll be able to find one of the forces through statics. In that case, you find the other one pretty easily. Statically determinate.
I found it.
Oh yeah, is it dynamics?
It's actually in dynamics. So
okay. We'll be getting to dynamics next week. So
okay, my bad.
Mm-hmm.
Yeah, go ahead.
Another big part of statics was trusses, if everybody remembers, which, well, those of you who are taking finite element analysis, you know the difference between trusses and beams, and it makes you want to cry sometimes. But to find the forces. True. Whistler makes us want to cry. There are two different methods to find the forces on a truss. There's a method of joints and a method of sections. Method of joints is pretty good if you're given a section of a truss that is not too far away from one of the reaction forces on the edges. Whereas method of sections is useful if you want to divide your truss in half, and you can find your forces. You kind of have to work your way up through the truss to get the resultant forces. Typically, method of joints should get you where you need to go all the time. It can be kind of slow for certain problems. We will see a problem with method of joints later. Okay. I believe. And then we have all of the centroids, moment of inertia, radius of gyration equations. And that's it. So that's the FE handbook for statics. We may be referencing it. Let me open up that. We may be referencing it as we go through our problems. But for now, we will start working on those.
May I make a note here?
Nope.
Yeah. I'm gonna do it anyway.
Where are you gonna know?
Have all questions for the end of the presentation.
Save all questions for the end. Okay. Where are you gonna write? Are you gonna annotate?
Oh no, I wasn't gonna annotate.
Oh, if you have a note, go ahead.
Comment. Yeah. So what I did see was I think you're only gonna see one pulley equation. You're only gonna see one truss problem. My bad. One pulley, one truss. But you're gonna see a lot of these kind of problems right here. Ones you're doing for chapter 22.
Yeah.
Yeah, that's heavy.
Gotcha. Well, I mean, I haven't got a lot of beam problems, so we're gonna go through a lot of those. Some of them can get pretty intense looking, especially with a lot of dimensions, and it could be confusing on figuring out what you need to do. But hopefully, we should be able to get through these fairly fast. There's also some problems like this one right here that you basically. Oh my gosh, please. I'm not sure what's going on. This thing is freaking out. Okay. Problems like these, where you can actually solve it in like 10 seconds and not have to do any calculations. It only works for some of them, but with enough intuition about the problem, you kind of can solve them without having to do too much calculation. Again, that's not all of them, but once you can save time on, we want to save as much time as we can, so we have more time for the rough ones, which is going to be fluids and thermo, most likely. Okay, let's do this. Can I make myself a little bit thinner? That's great. Okay. So we have, let's see, loading shown requires a clockwise resisting moment of 20 Newton meters at the support. So we know that there is going to be a requirement of 20 Newton meters here to prevent this thing from breaking off. Okay, what is the force F? We want to know what this is. Okay. So if we do a moment sum, it's like, say, the sum of moments about this point right here. We'll call that point A. Do the sum of moments about A. We know that that has to be 20, right? So you can say 20, negative 20. Let's say this is equal to 0. It is negative 20 plus, now we're going to be doing some moment calculations here. So we're going to have what, 75 times the moment arm, which is 0.5 meters, 75 newtons, times 0.5. My participants, this is in the way. Your guys' faces are in the way too. I can't see your faces anymore. All right. What else we got? We got F, right? Plus F times another distance. But interestingly enough, we have 15 too. 15 and F have the same line of action. So question to you guys, do these both contribute to the same moment, or do they have different moment arms? 15 and F, what do you guys think?
Anthony, do you want to take that, or?
I'm kind of thinking about it. It's been a while since I've taken statics, but right now I'm going to say that maybe the 15 wouldn't contribute as much to this problem, because I'm thinking of it from like a practical standpoint. I can see the 15 working on this, that top piece, and really having a moment at that top piece instead of the full bar.
Right. So I mean, I guess if we put like, what's the moment right here?
Yeah, then
15 would have an effect. But you don't think this is going to have an effect on the whole thing?
I don't think it.
That's fine. We'll see what
noticeable
happens.
Effect.
So if we'll do F times, let's see, 1.5. And then so we technically, with tentative right now, we have plus 15 times 1.5. Or not. Yes or no, that could be there, or not. I mean, another thing you could do is F plus 15 times 1.5, I suppose. Would that give you the same thing? Yeah, kind of would. Just a little more simple. Or not expand. But since we want to solve for F, we are not going to look at it like that. Okay, so let's see what we get for F, including 15 and not including 15. Let's see what the answer is. So we have F. I'm going to draw back. Good. Negative 20 plus 75 divided by 2. It's about 37.5. Plus 15 times 1.5. 22.5. All these are in units of Newton meters.
Yep.
And now, if we move the F to the other side, equals negative 1.5 F. So 22.5 plus 37.5 minus 20 divided by negative 1.5. total of, does it give us negative 26.6?
Yeah.
Okay. And if we take out that 15, that means this term wouldn't be here.
Yeah,
Well,
and we wouldn't. Yeah.
37.5 minus 20 divided by negative 1.5 gives us a number. It gives us negative 11.6, which is not even close to a choice on
No.
here. So it looks
Yeah,
like we
I
do
did it again.
incorporate the 15, and the
Cool.
reason is that is we consider this whole thing to be rigid.
Oh, okay. I get you.
So if we consider it to be rigid, this will affect everything
thing.
below it as well. Yeah,
Okay. Yeah.
it's good. It's good. So what's
It's
the
around
closest to 26.6? I believe so.
Because we're assuming that here we've written it, and I did the same thing. We're writing the downward forces as positive.
Yeah. I made it.
Because if you switch it, if you're saying clockwise is positive just by right hand rule.
Yeah, right.
And
So
then
basically, it depends on what you consider to be positive or negative.
Yeah.
But regardless, this should be the opposite of this.
Yeah.
It's strange that they use up and down as their directions. That's kind of weird to me.
Yeah, instead of positive and negative. Well, I guess it just depends on, like you said, what you
Like
consider
imagine
positive.
if you made that 20 positive
Mm.
instead of negative, how would that change things? It gives you a much different number.
Yeah.
Gives you like 53. So at least that's not a number that's on here. So
Yeah.
again, but if that was positive, I think these just would have to be opposite.
Yeah.
Yeah.
And then of course too, maybe the
Okay, I guess since the forces
that
are pointing down, if you made this 20 positive, and since these are going downwards, negative y direction, it'd work out that way. This just happened to work out this way as well.
Yeah.
Yeah, but that's the correct answer. Good job, team. Way to go. All right, we have another one here. For the member shown, this 700 Newton meter moment is applied at point B. If the member is pinned so that it rotates around point B, okay. What counteracting moment must be applied at A to keep it in equilibrium? So we're looking for a moment here, MA, to keep it in equilibrium. So what we got to do is, we know that there's a moment in this direction, which is moment of B, right? Meaning that this thing wants to spin 700 Newton meters moment in the clockwise direction. We need to calculate all of the contributions from these forces so that we can find out which forces are helping this B moment and which ones are opposing it. Which ones are making it go the same direction, which ones are opposing it. You can already tell that this force at A is going to contribute to this moment at B. This one at D will oppose it. This one at C, at least the X direction C, that's an interesting one. It goes right through B, so I don't think that one contributes to B at all. That one will contribute to A though. And then we have this other one at C going in the negative Y direction, which will definitely contribute to B positively. So let's see what we can do here. Let us do if we do a sum of moments, I guess B is a pretty good choice. Not sum of B, sum of moments. We have, let's keep our signs consistent. That is we'll call that's the clockwise direction, so we'll call it negative 700. What's contributing to this? Plus negative 150 times 4.
Yep.
That's not a C, it's a parenthesis. There's that one. We have a component of this. This is going to be, I think I need to make sure my signs are correct here. Since this moment is going to be, no, it's negative, so that actually works. That's fine. It looks like we're going to have do that. The x component of this is going to oppose B, and the y component is also going to oppose B. So we're going to have to get these components of this 300 Newton force to find out how it is affecting. How I would normally do this is I would find the angles, but I'm pretty sure there's a way you can do it without having to do angulars. Like, I mean, you could get the angle using an arctangent here of 12/5, I believe. It's like 67.
There's a way to do it without getting the
Without having to use an angle?
yeah.
What would
Use
that
the
be?
triangle, right?
Yeah, Anthony's on the right track.
If I'm not mistaken, because it seems like the triangle kind of stumped me, but if you wanted the y component, it was the y component over the hypotenuse times the magnitude.
Would that be
Is
what,
that-
12/13?
I believe so, if I remember correctly.
So because that force is in the hypotenuse, right?
Yeah.
So if you were to calculate the y, Anthony, what do you usually do? You would do the force sine theta, right?
Correct. You would do sine to get the y.
Yep.
But we have sine theta, which is, well, whatever that is, 12/13.
Ah, I see what you're saying.
Oh,
So it's
yeah.
basically the same thing.
Yeah.
I'm running out of room, so I'm going to go to the next line. Plus, so it'd be 300 times, what is sine? Opposite over hypotenuse, which is 12/13.
Yeah, you had it right.
Times the moment arm, which is what? That's the y direction? No, that's
It's
this
perpendicular.
is y. So this is going to be 4.
Yep.
That's plus. We're also going to have plus
So
another opposing.
Anthony,
300.
what would be the x one?
The x would be 5/13 times 300.
Times. And then what would be the moment arm?
What's the moment arm?
2, because it's in
Yeah.
the x direction.
See? Yeah, there you go.
Nice. Nice. Let's see. What else? 150 is not contributing. We do have that 200 up there. They're both going to contribute to a positive, or sorry, they're going to contribute to, this is negative. So it's going to go in the direction of the B moment. So this is kind of doing this kind of motion. This force is going to make this shape want to go in that kind of direction. So it's going to be minus 200, the y component of this.
3/5.
Yeah. Moment arm.
Why is it
It's
the
along the same axis.
real-
So
Yeah,
you
so
shouldn't have to worry
the
about
y component's not actually going to have a contribution,
okay.
but the x component will, which is 4/5, and that's going to be 8, right?
Yeah.
Yeah, so the y component is along the same line of action as this moment, so it doesn't have a contribution. Same with this 150. All right, so with that, we can actually get what this is, what the net, moment from all these forces is going to be.
About
Oh,
negative
right.
873.
Did you calculate it?
Yeah, negative 873. Around there.
All right, guys. I do have to leave right now. I have to actually get my I have to do a couple of things and get my fingerprint scanned for my fucking EIT. So.
All right. Nice having you here for the 30 minutes.
Yeah.
Great insight.
Glad to help out. Couple of things. If you want to market this even more, email Marina Crawford. She's who I talked to last time, and
I've been talking to somebody regarding it, so
cool.
Christina as well. So we should be good.
Dynamics next week. What are we tackling?
Yep. Dynamics, kinematics, kinetics, vibrations.
Oh, nice. All the best stuff.
Yep.
Okay. All right, guys. Good luck today.
Thanks. See you.
Have
All right. Doing some math here. What did you say you got, Mr. Kent?
Negative 873. Let me run that again. Do that 12.
Well, so you don't mess up your calculations. This should be about 1242. So meaning that if that is the total amount of moment that is going to be going in the clockwise direction. So A needs to have at least this much going in the opposite direction in order to counter it. In that case, that would allow it to stay in a static equilibrium.
Let me just rerun and make sure I can get that.
300 times 518 times 2. Minus 700.
Where's there? Yeah, I mean, it still comes out as negative, but now I get 1241.
Yeah, that's right. So as long as you don't do your math wrong, you should be able to get the answer to this one fairly straightforward.
Yeah.
It's
They put
basically
some-
just doing some little something.
Put some fake answers on there then.
Oh yeah, yeah. That
'cause-
that first one you got, the one that was near 890.
Yeah.
It's kind of scary. You just happened to mess up just so you got the wrong answer. All right, let's go to look at this one. This is on one of the quizzes, actually. 285 kilogram plate is suspended horizontally by 4 wires of equal length. Tension on each wire is equal right now. If D snaps, like this one right here, the tension in the 3 remaining wires is redistributed. Determine the tension in each of the wires after D snaps. So this is another one you technically could do intuitively if you're if you know the physics of what will happen when D snaps. Otherwise, we can solve it how we would solve any other statics problem. I'll go over the statics method first, and then the intuitive way after. At least the way I was able to do it intuitively. Then again, even if you do it intuitively, I'm not sure why I don't have the answer choices here. Do I have those somewhere else? I guess I don't. Well, that'll make explaining the intuitive method a little more difficult. That's okay. All right, so let's do this. What can we do here? If you remember correctly, in statics, you can take the moment about not necessarily just a point, but you can take it about an axis. So let's do that. Which axis you guys want to do? Pick an axis that's doesn't touch D.
Doesn't touch D.
Because D doesn't help us here.
No. So we could do like the moment about the x-axis? Or
yeah, technically, but what I'm trying to say is like you could do an axis like AB.
Oh, I get you. Yeah, okay, yeah. We'll do
So we
AB.
do some of the moment about AB.
Sure.
Everything within the line AB is knocked out, so we can get what we have. One, we actually do have a weight here
Right.
of 285 kilograms times
9.8.
half of this, right? It's in kilograms. So that's already a mass. Yes, we make it a weight by multiplying it by 9.8. Or make it a, yeah. We have that. And it's going to be about 4 because we assume it's in the centroid of this square. Since it's a plate, well, it's 4 equal length. So tell us that in the problem, it doesn't tell us if they're all equal size, but we can see that they're both 8 meters wide. So we know that it's a square. So we know that the centroid's going to be there.
Right, in the middle.
The moment arm for the weight is going to be about 4 meters. I use 10 to round. I use 10 for gravity, just so I can round easier. It makes a little calculation if you're using a calculator.
Okay.
A little easier.
Yeah.
What else we got? What else we got? We're gonna have yes. What is it? Question?
I just I didn't know if we are gonna get the values right now or not, and also it's 285, not 289.
Oh, you're good catch. Number 89 is too apparent. Now we we can also get the let's see, C, correct? There's a force, a tension in C.
Mm-hmm.
Tension, yeah, tension. Could be tension. So that's we're gonna call that. I'm just gonna say plus for now. FC times 8. Does that make sense?
Yeah.
And I
It's
believe
a
that's
moment
everything we
about
have there.
For that moment, yes.
Mm-hmm. So we can solve for force in C. What is force in C? $2,850 times 4.
I got about 1,400, give or take. 1,396 is what I got.
Okay, yeah, I got 1425 because I rounded gravity to 10. What'd you say you got? It would be negative. 1396?
Yeah, it should be negative. Yeah, negative 1,396.
All right, cool. We got FC. You guys can't see the answer choices, but the answer choices, basically all they say is like F. Let me see if I can get it really quick. Let me pause that. The answer choices. It'll be easier to show. I have that.
Yeah, then writing them all out one by one.
Yep. Here it is. Nice. Okay, we're back. Here are the choices. Yeah, so basically it's asking TA, TB, and TC. It wants to know what the forces in these three are. So we got one, what, negative 1396?
Mm-hmm.
That's for
Okay.
C. So
Yeah,
that
we can
basically means
rule
it could be C or B. So that means we got to get one more. All right, now what's the moment about?
Go CB.
CB. Well, we're going to have the same number from here, 285 times gravity times 4. And now we're going to have plus FB times 8.
Or FA.
Sorry, not FB, FA.
Okay, yeah. So then that means that F or tension in A is going to equal tension in
Yeah, doesn't it? So
C. It's a square, and all the values are the same.
mhm.
So right now it looks like B.
B is the correct answer. Tension in B is actually 0.
Cool.
So this is where I said you can do this intuitively. Basically, if you do this intuitively and you know that if D fails, B actually will have no force on it because A and C, if you think about how this will look like physically, you have a weight in the middle, D collapses, so this force is gone, so this thing tends to hang off this way.
Mm-mm.
And if you notice, this B point has the ability to move upwards, and if B moves upwards, this cord becomes lax, meaning there would be no tension in it at all. So you can immediately tell the only one of these that has 0 for B is choice B. So you could kind of find this answer immediately off the bat if you knew what this looked like physically. Which also, you know, it's always nice to actually solve them out too. But
Right, but it's a good,
if you have the intuition to figure it out without that, you can make it a little faster. But yeah, that's that problem. It's a pretty nice one because it shows how you can solve them intuitively as well. Oh, this one also doesn't have the answer choices. Wow, I failed this time. It's okay. Let's go get them. This one, I don't know if you can still see what's there, if it's just paused, but
yeah, I can. Yeah,
you can still see it.
yeah.
Okay, so it's asking if you were to move, if F2 were moved to point B. So you're moving F2, which is negative Y direction, over to point B. Oh, well, I can't really show the answer for this one. I'll show the correct answer. But we have 4 choices. We have this thing could be replaced by a force only, a force in a clockwise moment only, or a force and a counterclockwise moment. So we could be replaced with force B, which is this thing's just a moment.
Yeah, was it? Yeah.
Clockwise moment. C, force and clockwise moment. Or D, force and a counterclockwise moment. All right, so let's see this force 2 right here. It's going down this direction. This is one of those features of statics where you have to know what happens to this force if you move it down here to point B. You can see they're in the same line of action, but what does that mean? So if you look at it like this, let's say we move this force F2 over here near A, this line of action of A. We move that a distance that's perpendicular to its current line of action. See, because of that, we've created our artificial moment arm, right?
Yeah. Just
So-
now it's off by a distance of L2.
Yes.
Now you can
So
have a
we would
moment.
have to include a moment with that.
Right.
Since we know this is in the same line of action, we're moving it just straight down its line of action.
Yeah.
It's not going to require a moment.
So it
to
should just be A
compensate.
then.
So basically, yeah, knowing that, it cancels out all of the other choices, and we
Yeah.
know that it's going to be A.
I seem to remember that from statics. It was like if there was a moment, you can just kind of put it. If it's on the same line of action, you can kind of just
You
shift
could
it.
move it down that B, that whatever part. Yes, exactly.
Yeah, just to make it easier to like visualize and all that, but it doesn't change anything.
Exactly that, and that's that. Pretty nice and simple. Nice conceptual one.
Yeah, and that
Like,
one
for
looks
example-
complicated on the surface.
It does. It looks like a box. You're like, oh gosh, what am I going to do? There's so many L's. There's an M. There's F1, 2, 3. Now, if we moved this F like back here or over here, we'd have to incorporate a moment of what direction we would make this thing spin about this line of action, which would probably be this direction, which looks clockwise to me. But in that case, it'd be a force plus a moment. I don't actually know if there's a case where you just create a moment. Oh, actually, no. Yeah, if you could just create a moment if you just move the force.
If you were to like rotate it, I guess, like if they were to ask like, if you make F2 in the X direction, then
Yeah,
you know,
yeah.
then it could,
Yeah, like
it would create a different. It would just make a moment.
All right, cool. Oh, cool. We get to see another problem that we can solve intuitively. So, you know, the way I solved this, I looked at it, we're asked for, we have a simple truss, all joints are pin connected. The reaction at point E is 1220.6 to the right. We have a reaction in this way, 220. A vertical reaction at A is 830 and upwards. What is the forces in members AD and ED? So we have a 50 down here, 830 up reaction, and a 1220 reaction here. So the only two, there's two applied forces here. There's a 50 and then there's three, 50, 300, and a 600. All of these are creating a moment in this direction. So look at the structure. What happens if there's a very strong moment in this direction and this sort of thing bends a little bit? This point BD is likely going to move downward, right?
Right.
Even just a slightly bit. And if this moves downward, what happens to these two AD and ED? There's a D here.
BD moves downward or point D moves downward, and that should put, you should have some sort of tension in AD, especially because you have a force moving in the opposite direction.
Yes. Yes.
So AD should be in tension and ED should be in compression then.
Right. And look at the answer choices.
Okay, so we can rule out two of them. We know it's going to be either A or C because tension and compression. And then
Actually,
I would, right?
No, it can.
Oh
only
no, that's
be,
tension. Oh
Yeah,
it's only
it can
C.
only
Alright.
be answer choice.
C.
Yeah.
Yeah, because I didn't see that A was tension. I thought it was also tension compression. And
What?
even then, if it was tension compression, I was going to say C anyway because E had a higher magnitude than A. So that would just tell me that FED has to be higher magnitude than
Exactly.
AD.
That's the way you can do it intuitively. I'm about to go through the way you can solve it without having to do that. And I don't know what just happened to my pencil. What the freaking heck?
I think you're using a different.
There we go. Now it lets me select it. Sometimes it doesn't let me
Oh.
select the other color. I'm just so confused.
I wonder if Whistler has like issues sometimes. And
Maybe he does. But yes,
Yeah.
this is also the correct answer.
Yeah.
You didn't have to do any calculation at all. Well, now we're going to go through what calculations we need to do. But when that was shown to me, I'm like, I got this. And it just so happened to be the correct answer at that point. So that's pretty cool. Okay. Solution for this. What should we do first? We have a lot of forces. We can do some sum of forces in different directions and see what we can get. Sum of forces in the x. Let's just do the sum of forces in the x direction, yeah?
Okay.
What do we have?
We have the 1220 to the right.
Okay,
Oh, that
what is
positive
that?
1220.
That's F E
E.
X
Yeah.
plus this 300, right?
Yeah, that should be
With
4
the-
over 5 times 300. 240.
Mm-hmm. Do we get a total here?
I can just do that, yeah.
I think it should be
1460.
1460.
Yeah.
Oh no, wait. Wrong. Mistake. I made a mistake. We are okay. This is going to actually be. That's right. We're looking for. This is a reaction force. We're looking for the force in this bar, right?
Right.
Whatever direction it may be. So what we actually want to do is have this E, point E, actually ED, right? ED, which is going to be that force, FED times the cosine of this angle. That makes
Okay.
sense?
Yeah. So would we use the oh wait, no, because that's on a right triangle. So would we use the 4 over 5 again? Can we say that it's symmetrical?
No, we have to use, we have this 4.25 is the length. So we have to find what the lengths are of the other two dimensions. ED.
ED is oh, okay, I think I get it. Instead, how about 3.75 over 4.25? Because the way you've drawn it from E to, I guess, the continuation of line DB, that should be 3.75.
Yeah. So
Yeah.
3.75 divided by 4.25.
Yeah. Just use that same triangle method. Don't have to worry
Yeah,
about angles.
exactly. And that will get us that. And now we add that E and the X. So this is our unknown. We want to solve for it, and this is equal to 0. This is 2000. No, 1 to 20.6. Right? Okay, cool.
Yeah.
So we can get FED here, which is going to be negative 1220.6 divided by that fraction. Should be what, 13?
Yeah, 1380.
1380, and then
Yep.
that's going to be negative.
Yeah.
Hey, look, we already got one of them, and we got it in compression. So ultimately, we still know the answer exactly just after calculating that.
Yeah, because we
So
know that it's
technically don't need to calculate anything else.
No, because you know that it's you can say that it's shortening or whatever, and then that's the compression. Yeah.
And then every other answer has ED as tension for the wrong value. So
yeah,
but we'll go through it anyway just because we can.
Yeah.
But technically, this problem is fairly short. But if you wanted to get the one for what is it, AD? Yeah, AD. We're basically going to do the same thing, but we're going to do sum of forces in the Y. What do we got?
Again,
Force AD Y direction is going to be
2 over 4.25.
2 over 4.25.
Yeah. Plus here we can just use EY, or AY. Sorry, not EY. AY.
AY. And CY. That's minus CY. And also minus 300 times 3/5.
Mm-hmm.
So FAD, FAD. It's the new FAD. What is this? This is 600. No, it's 830. This is 600. 830 minus 600 minus 300 times 3/5. Move to the other side, negative 50. No, is it negative? Oh, no. Divided by 2. Oh, yeah, we get 380.
We're still working it.
I didn't miss anything. Oh, crap, I missed that 50.
Oh, there's a 50 there. Okay. Minus 50.
These are things that cost you on the exam.
That's where if you already sum all those, then it's 0. 830, 600, the negative
Really?
300. Yeah, that's all zero.
Ah, it is zero. Did I screw something up? Interesting. Let me check. Hmm. Oh, that's the mistake. Okay. So what I did, no wonder it's zero. I accidentally did the sum of forces across the whole structure when we should have only done the sum of forces about point A. If you do the sum of forces in the y direction at point A, we only look at this point and we have what? There's a force here, there's a force there, and there's a force here. There's only three forces. This is one of them. It's going to be plus 830. And then what's the force? What's AE? Do we know AE? We don't, do we?
No.
Well, that's actually we do know. I think.
But we can get it because if that's zero and we can find the y component of FED, right?
Oh, right. Okay. $830 is AY. I put AE. No, 830 plus 830.
Yep.
830 minus FAE times, right?
Yeah. It's
Okay.
just getting
So we
it
just
right.
gotta get FAE. FAE we can get, okay. Is FAE FED times sine of the angle?
That's what I'm thinking.
That's that would be
1383
what's
times.
the height of that? The height of this section here, we can just do the triangle again.
Again, yeah. So for
What was this? 3.275.
3.75.
Stop going down. So you can do some Pythagorean theorem to figure that out.
All right. Okay. I got it. I did the wrong calculation.
It's two. It's two, isn't it?
Yeah.
2.
So if you take
So FAE is going to be
FAE, I got around 6 something. 650.8.
it's going to be about 1383
Yeah.
times 2 divided by 4.2. 650, yeah, 0.8.
Yep.
830 minus that times 4.25.
Yep.
You
You get 380.
Yep. But you really shouldn't go through you should not go through the process of getting this and doing this at all. You should not go through this process if you already get this one, which was a much simpler calculation than the second one
Yeah.
to begin with.
Yeah.
To get that, you know, as compression is the only one with it. You just go through the answer there. That's what you should do.
Yeah. It shouldn't take you that long because either you look at how it's moving mechanically or you just calculate ED.
Quickly calculate the first force, ED. Yeah. Unless you get unlucky and you decide to calculate AD first, and then you realize, oh, I need to have ED before I can get AD. and then you cry a little bit. But
And then you get ED, and it's all better.
yeah.
Because you figure out what the answer is.
So I mean, technically, that's the worst case scenario is you try to do A first, AD, find out you need AE, go to get ED, discover that you have the answer. And hello, it's a truss. Welcome to Truss Land. Okay, how many we got? This problem, another truss, and then a pulley. Oh no, it's a centroid. Okay, we'll get through these pretty quickly. For a truss, what are the forces in AC and BD? This one is not a short problem. Since trusses typically take a bit, since you have to do a lot of calculations to get to the answer. We want AC here and here, and BC, which is no BD. Sorry, here and here. Okay, how do we begin? Whenever you have a truss problem and you're given not given reaction forces, the first thing you should do is get the reaction forces. So, or at least the one on the side that you are going to be working on, which for us is F1. So let's get F1. We're going to have to sum the moments about point H.
Yep.
Do you understand why?
Yeah, I remember, especially in deformables, if you take a moment about a point, then you get the other.
You get the other side. Yep. Moment about here. What do we have? We have 5,000 times 8 times 3.
24.
Plus minus F1 times, well, the whole shebang.
Yeah.
And we can get F1 to be a number. That number is going to be 3750 if you do the calculation. And don't calculate it wrong. Next thing we're going to need, since we want AB, we're going to need to know what this angle is here in order to do trigonometry.
We have that height from VC is 8/3.
Yeah, 8/3. They're both 8/3.
Okay, cool. So that means if we just want that angle,
it's going to be 8/3 is the opposite. The adjacent is 8. It's like about 18.4 degrees. So for this one in particular, we're going to do the mod, which is the method of joints. And we start with joint, AB, or joint A, or pin A, whatever you want to call it, since it's pinned at the edges. If we do the sum of the forces in the y direction, we can use this F1 to our advantage. It's equal to 0. It's also equal to F1 plus link AB, but sine of 18.4. And with this, we can get force AB. Does this make sense?
yeah.
Which equals F negative F1 divided by sine of 18.4. And with this, we get, what is it, negative 11,880. 880. Okay. And it's negative, so it's compression.
Right. But it doesn't look like they're asking for that. So for here, I can see that maybe our answer is A. That's the one that's closest.
This is AB. This is asking for AC.
Oh, they're asking for AC.
So we got AB. Yeah,
Oh.
It's asking for AC. We gotta check AC now. But we need this one because we need this one in order to get AC, which is what we get right now. So we still continue with method of joints at point A. Now we did sum of forces in the x direction. We needed that so we could get the x component of it. Because we need the x component of AB to figure out what's going on in AC. This is going to be what is it? F AB, what we just got, and we're going to have cosine of 18.4 plus AC, which is going to be the basically, why am I messing up names here? I'm just going to be consistent. Let's call it AB. Oh, you're not going to let me choose it again. Okay. AB, cosine of that, plus AC is sum of the forces in the X, which is 0. So AC is actually just the X component of AB.
Right.
Negative, of course, which I think cosine of 18 is negative. No, that force is negative, so it's going to give us a positive result, which is what? 11.
I
11.
got about 11,272. If you use the cosine, it's 11,272, and then if you get the hypotenuse of that, it's 11,270. So it's about the same.
Okay. Awesome. Now let's look at our answer choices real quick. AC we got was in tension, which corresponds to one answer choice. So at this point, you should choose answer A and just move on.
Yeah.
Because all the other ones don't really compare at all. 1100, that's really funny. 0, yeah, they're not going to be 0.
No, there's something going on at A, so it can't be 0.
Yeah. So you honestly here, you should just stop and continue on, because I'm going to say right now, the calculation to get BD is quite a bit longer than what we just did.
Yeah, because you have AB, you need to have.
You need BC.
Yeah. BE.
And you're going to need BE as well.
Just to get BD.
Yes, because they're all at angles. It's kind of a mess.
Yeah. And you don't have anything on the the A side to get BE. So I feel like for that one, you'd probably have to get F2 and then go from.
Literally, this is what it's going to look like. You're going to have point B right here. You have BE going this way. You have BD going this way. And then you have AB coming this way.
And BC going straight down.
And then a 5K up here.
Yeah.
Yes, and a BC.
Yeah, and you can't say that BC. Yeah, so you'd have to.
It does come out that we find out that BC is actually a 0 force member, so BC is actually 0. But that's pretty helpful. It allows us.
You'd have to find that though. You couldn't just be like, I deem this a 0 force.
Yeah, what you do is you go to point C. Let's go up, yeah. You go to point C, and you're like, okay, what's the sum of forces in the X direction and the Y direction at point C? If you look at localized point C, just point C, X direction, there's nothing there. At that point, because you have AC. What was AC's intention?
Mm-hmm.
And there's going to be an equal opposite reaction from CD, meaning that C is kind of just in the middle, and it's in the middle of both of those, and that's what we call a 0 force member. So that's not going to have any force on it, which is cool. It drops out of our little diagram. But I don't think we need to go through the rest of the calculations to get the other ones, since we know we already were able to do it. But just in case anyone's curious, what we would do here is we do a sum of the force in the X and a sum of the force in the Y. And one of these would give us an equation that tells us AB plus BE plus BD is equal to 0. This one gives us another equation where basically we use this relation in some algebra to get that BD is, negative 7,900.
Yeah.
But this relation is important because we know this is known. We have one equation, 2 unknowns. We go here, we get our second equation, 2 equations, 2 unknowns. You solve for them, and you get BD, which is totally fine if you want to do. But in the FE, when you're on a time crunch, I don't recommend going that far just to confirm your answer.
No, when you already have it, a pretty good guess on it. Just go for it.
Yep. we have another truss here. Force in member DE. Excuse me. Okay, DE. How do we do this one? Should we do method of joints or method of sections? I believe this is a method of sections because we want what? DE, right? DE is way over here in the middle of the truss. It's not attached to any of the reaction points.
Right.
So where should we cut this thing is the question.
I don't remember method of sections much.
Method of sections is a little more complicated. Okay, well, we're gonna, looks like since it's going onto this side, we're gonna be dealing with likely this right half of the truss. We're probably gonna wanna cut this thing right here.
Okay.
So, and if we do that, we'll have, this is gonna be what, DE. This comes down here, comes over here. This is point C. This goes this way. Yeah?
No,
What's
I
it
just
look like?
yeah,
Okay, cool.
that side. We should deal with the other side, shouldn't we? The one with the 25 kilonewton.
That is also that's also there. But let's look and see what we got here. If we use no, we're actually gonna want we're gonna want to use this left side. Since we've cut off basically everything from this point to the left has all been like sliced up, that's gone.
Okay.
We have everything over here on the left side. Also, this A pin is nice because we have two, we have this direction and this direction pinned, so it helps us a little bit. So we should get what is the force in the Y direction here, because that will help us. So we have to do the sum of the moments about G to get A over here. So what do we have? Negative 25,000 times 30.
Some of the moments about G is just negative 25,000
Right.
times 10.
Right. Gotcha. My bad. And now we got FA Y times 30.
Yeah.
That one's times 30. We get FAY. So we get this divided by this 25K times 10 divided by 30, which is about 8,333.
Yep.
Okay. So if we take this thing right here, let me just draw the left half of this thing. A, B, C, D. If we do the sum of the forces here in the Y direction, what do we got? We have this reaction force, and we're also going to have a component from this D. This is DE, right? DE.
Yeah.
So in that case, we can actually get DE from this. Sum of the forces in the Y, positive 8,333 plus DE. Now, what is this angle? What angle are we looking at? We have that angle.
10. The full thing is 15.
This is cut in half, right?
Right.
Okay, so this is 5.
5.
This is also 5. And if this is 5, this here, this is 15. It's 5 over 15?
Yeah, arctan.
Yeah.
18.4 again.
18 point. Wait, really? That's really funny.
Right?
Oh, yeah, I guess you're right.
Opposite over adjacent.
Yep. Well, actually, we don't even need to use the angle if you didn't want to, but I mean, if you want,
Right.
you can use it, which is just sine of 18.4 or 5/15, whichever you like.
Well, we'd have to get the hypotenuse for that, I believe.
No, we have the. Oh, true. Wait. Maybe I'm looking at this wrong.
Yeah, because 15 would be, I think, the way I think it was always taught to me is like 15 in this case would be like from a point to the other line. So it'd be like from F to the line EG or from E to the line.
Yeah, you're
EF.
right. That is the 15.
Yeah. So if we wanted to use the triangle method, then we'd have to actually get the hypotenuse of that. I mean, it's not like it's that big of an equation or anything like that. Either one should work. Should get you roughly the same answer.
Yeah, they're slightly different, you're right, but yes, they should be similar.
Mhm.
What does this
And
give
then
us? This gives us
Should
the.
this be negative? Should DE be negative?
It should be in tension.
Okay, because the way I'm thinking is I'm picturing at line DB, I'm picturing I guess at point D, I'm picturing like a XY axis, and I'm seeing like DE coming off of the X axis
Oh,
clockwise.
this should be, yeah, you're right. This should be negative here.
So it should be. I mean,
Yeah.
it should cancel out. Yeah, it'll cancel out anyway.
If this is negative, then it fixes it, because it is going to be in the minus y direction.
Okay.
At least the way we drew the slice. So with this, DE comes out to be around 2778. Oh, that's just the x direction of it. This is dx.
T7. Oh, okay, yeah. Or Y.
Sorry.
Okay, DEY.
Oh, wait a minute. I think I've done something wrong.
Yeah, because I'm getting 26,399.
Let me see. Okay, in the y direction, DE. Come on, thing. Okay, looking at the solution, the way that it's done is it basically they don't use they have just for the y direction. It's just this. There's no factor in with it. So that's where they have.
Okay. Oh, okay. But then you should be able to get the full force from there if you have the Y.
And then with this, you go to the sum of forces in the x. Or you don't have to do that.
Yeah, you should just be able to do what arc sine, right? Of 18.4 times.
Times.
Oh wait, no, maybe not.
Is this is what's 5/15, which is arctangent, isn't it? Or tangent. Yeah, it's tangent. The tangent is 5/15. If you do that to the x component, you get the y component. Sorry, the y component, you get the x component.
Yeah.
And then you can get dE by, squaring the two of them.
Force in Y is equal to. Oh yeah, but I tried that and I got like a massive number.
That's interesting.
Never
I'm not sure why they do it like this. In the forces in the y direction, they don't use a factor to accommodate for the angled bar. Maybe that's due to the fact that it's a section. It's sectioned off.
Forget about C. See, yeah, that one's kind of weird to me like this whole problem, because I figured there should have been a way you could get the force from DEY, because there's a way to turn the force into the X and Y components.
Yep.
So I'm like, well, maybe you can just go straight from the force from DEY back to the force.
You'd think.
But you can't, apparently, because I tried it and I got this massive, like, monstrous number.
Well, method of sections is a little not
Different.
as intuitive as the other ones, but it doesn't really even tell you whether or not it's intention or not in these answer choices, other than they're all positive numbers.
Yeah.
Well, I mean, obviously we know it's probably wrong, but other than that, you have a pretty fair chance at the other three. All right, well, that's that. We can move on to our last problem then.
Okay.
Everybody loves moments of centroids. I mean, nope, just kidding. Moment of inertia.
About the x-axis.
All right, this is where we start to consult the book or the handbook, because these things can get kind of hairy. Okay. This thing has like 1, 2,
Is that technically its own shape?
3 and 4. So we got 2 rectangles, a half circle, and the whole circle, the circle with a hole.
Oh, this the middle circle.
So what we have to do here is basically find the moment of inertia for each particular shape here.
Okay, cool.
And proceed to do parallel axis for them all as well. Okay. Oh, hope you guys are ready. All right, we're gonna have section 1 here. I wonder if there's a way to do this that'll not take that long. How do we get the moment of inertia? What's the equation for a rectangle?
In the x direction, it's space times height cubed over 12.
Yep. What is the BH cubed?
I just did the full thing and I got 576. You want BH cubed?
576? This is 4 times 2 cubed.
Oh, I did 12. Never mind. Sorry. My bad. For some reason, I thought 12.
It's okay. That's probably why it was so large.
Okay. Let me redo that.
That's 4 cubed, right?
Yeah. Hat 2 times 4 cubed, which is 128 divided by 12 is 10.67. Yeah.
Yeah. Cool. Cool. We got that shape. At the end, I'm just going to write this here now. At the end, what we're going to have to do to get the total moment of inertia in the x direction, we're going to have to do the sum of all IXC plus the sum of all d squared a for parallel axis theorem. So we can effectively get all of these shapes into the same to make it so that it appears as if it's one shape instead of doing them all separately. So we're going to need to get a D and an A value for each of these. Distance that we're going to have for this parallel axis is going to be what? It's the distance to the center of this particular square.
To the center of that particular
shape, yeah, which is going to be to the centroid of it, which is 4/2, right?
Oh, okay, yeah.
Not the centroid, but half of it, basically.
Shouldn't it be 2/2 then?
Well, it's 4
Or-
centimeters, which is the
Oh,
length of
okay.
it.
See, I wasn't quite sure what half we're talking about. If it's like
Okay, yeah.
half X or half Y, I guess.
I wonder, does it show the D value in does it show the D value in that table?
It shows where the centroid is and the height and the base.
Let's see, statistics, product of inertia, radius, gyration, yeah. And A is 8 cm squared. So D squared A is going to be 16
Oh, 2 times 4. All right.
cm. Oh, to the 4. That's actually squared. Yeah. All right, cool.
Okay.
Number 2 is a rectangle, huh? Yeah, it's a rectangle with a part of it cut out by the thing. What is IC? Still the same, BH cubed over 3. I think what we're gonna do is we're gonna just treat it as if it was a full
Yeah.
rectangle, and we're gonna cut the circle out at the end.
So I did that one. I get about 13.02.
Yep, I agree.
That's 10 times 2.5 cubed over 12.
I
And
agree with
then
that.
the D for that one, if we're going mid Y, I got about 3.25.
This one, what I have is like 4 plus 2.5 divided by 2.
Why do I keep doing the wrong one? Yeah, that's right. Right theory, but I did the wrong.
Because you have to also incorporate this 4 from the
Yeah, I
graph.
was
So
thinking that, but again, I used the 2. I used the X.
Yeah, gotcha. Whereas originally the axis is here, so the first one we moved it up by 2. Okay. The first one we moved it up by 2 centimeters, right? Second one we're moving it up by more than that, which is about
5.25.
whatever this is. It's 5.
Yep, 5.25. Yeah.
Next
And
one
then
we're
we
gonna
need
move it up even more, but yeah,
And then the area for that one is I got
it's kind of large.
25.
So D squared A, sorry. 689. You square the 5 times 25. Okay.
And then the third one's a semicircle.
Well, the third one is the sorry, semicircle, which I'm gonna have to look at the.
Yeah, it's a to the 4th.
Oh, wow, that's freaky looking.
Yeah, a to the 4th times 9 pi squared minus 64 close parentheses over 72 pi.
Not just pi a to the 4th over a. No.
That's for y. Well, it depends, because if you want IXC, it's that beast. If you want just IX, it's pi a to the 4th over 8. What did we use in the other one?
This book here uses this strange number.
Because if we were using, because on the rectangle we were using IXC, and that
Yeah.
was the B,
Gotcha.
the H
Okay.
cubed.
So basically everything on that's a constant except for the a. So what is the freaking value of the constant is my question. A to the 4th times, what was it?
9 pi squared minus 64, which is, that's the constant of just 24.83.
72 pi?
Oh.
That
divided,
over
yeah.
72 pi?
Yeah, let me get that. So 72 pi is 226. Let me just get the final answer. The D is 5, right?
D?
Yep.
For that one?
Yeah.
I don't
Like,
know
what's
what
the radius of the?
Oh. Sorry. It's 5. Yes, it is.
So I'm getting 677.
As IC.
0.1. Yeah, yes, XC. How did you
I
get
got
0.1?
68.6.
Yeah, I was getting 1 though.
You see?
Now let me try that again.
Did you multiply your pi?
9 pi squared minus 64. Take that number and divide that by 72 times pi. And oh, so what do I do up here? Weird.
This 4r over 3 pi.
Yeah.
You can also get. It's in the manual. Let me show really quick. For a semicircle here, we have the YC,
Okay.
4a, which is the same as r, in our case, over 3 pi. So that's what we use to, that's where that comes from. For the D. And now this will give us
5 divided by 3 pi.
6.5 plus 20 divided by 3 times pi. 0.62.
Oh yeah, 8.62, right.
A is pi r squared over 2. And then D squared A is those multiplied together, that one squared, so it's going to be about 2,919.33. Good, Anthony.
Sure. Yep.
Nice.
I didn't necessarily do that last one. I deleted a few of the values, but
That's okay.
should be right.
This one. If they ask something like this on the exam, this is a long problem because we have to do this tiny little circle now, and then we have to parallel axis them all together. Okay, IC for the circle, for an actual just a circle, is pi r to the 4th
Over 4.
divided by 4. And this is a 1, I believe. It's just 1, so it's pi over 4.
Okay, cool. That's 0.785.
Cool. We'll keep it like this. It looks nicer for now, but when we put it in the kit. D is just going to be all the other things. 4 plus 2.5. Actually, that's it. 4 plus 2.5 puts us at the center of this.
Yep.
So it's 6.5. A.
R squared, which is just going to be pi then.
So D squared A is going to be, take this together, 132.73. That doesn't look like that.
Oh, if it's 6.25 squared, right?
Yep.
Yeah, that's just 39.
Cool. 39 times pi. 39 pi's.
Oh, time pi. Yeah.
Okay.
Yeah, I get you. There it is. Yeah, there's a pi there.
Parallel axis time. IX is going to be our sum of all of our IXCs plus the sum of our D square A's. So if we go back and get everything we're going to have, we're going to have 10.67. I'll say them to you, Cameron. You want to type them in?
Yeah.
10.67 plus 13.02 plus 68.66 plus pi over 4.
Okay, so for the sum of all of the ICs, I'm getting about 93.14.
Right now we're going to sum the D squared A's.
Cool.
So add to that 16 plus 689
Okay.
plus 2,919.33 plus 132.73. Wait, minus those last, oh crap. Okay, we'll add it, just add it, and then forgot to make the circle one subtraction. But once you get that number, we're just gonna have to subtract 2 of the numbers again. That's okay.
When you add all those numbers, I get 3,850, but I can
Okay.
just redo.
So what we're
ones you
gonna do,
getting
subtract 132.73.
Okay.
I think we have to subtract it again. Yeah, subtract it a second time. And then subtract pi r over 4 twice as well.
And then subtract pi over 4 twice?
Yep, that should give us
Okay.
about 3602. Around 3,600.
Yeah, I got 3580.
Yep. Okay, so we got 3580, which is close to this one. Oh crap! Oh yeah, no, yeah, this one. Like those middle two are kind of close. All right,
Cool.
that's a long one. I
Mhm.
hate moment of inertia problems, but that's one that it could be.
Could possibly be on the FE.
And literally, this whole section in the practice book is just a bunch of different shapes. There's some that look like T blocks, like this, which you kind of would do the same thing, like double circles like this, a big square with like an empty circle and another square here.
Oh,
So
boy.
the method is all very similar. Well, we've done quite a few problems here for statics today. I believe we've definitely gone over some good stuff. If you'd like to take a look at the recording for this, and yeah, it'll be that. I would like to thank Mr. Cameron and for sticking with me till the end, and Mr. Ryan Blair, who was here earlier.
Awesome.
Did you have fun, Mr. Cameron?
Yeah, it was interesting.
Got to
It's a
relive
good-
some statics moments.
Yeah, got the nice blast from the past.
Yeah, and it's great because I'm not one of your instructors that, expects you to do a bunch of homework on this later.
Yeah.
We're just reviewing stuff for our own personal gain and our exams and stuff, which makes it that much less stressful,
Yep.
Very nice, very
Yeah.
nice. I will go ahead and stop the recording here. Thank you, everybody, for coming. Do take care. Leave comments in the bottom if you'd like some assistance on other topics, and be sure to subscribe to our channel for more fundamental of engineering and top of the pie stuff, whatever we decide to do. All right, take care, everyone.